On this last example, I'm using number 5 from the previous homework, and you'll see here that I again have added in some values instead of just saying if it was 0 or greater than 0. Initially, the spring is compressed over here. We're at a height of 0, so there's this elastic energy stored, and we're looking for the spring constant of that spring there that's storing that energy. So we know initially we have our 1/2 kx squared, and at the end, because it's frictionless, it is above the height of 0. So even though it's on a flat hill, it doesn't matter. It still has gravitational potential energy, and it shows that it's moving at 0.3 meters per second, so it has some kinetic energy, that 1/2 mv squared. So looking at what we know, we're looking for the spring constant, but we do know that our spring was compressed 0.3 meters. So that goes in here, make sure you square it. Then we have our gravitational potential energy, right? Our object has a mass of 0.5 kilograms times the acceleration of gravity, and it says that it's at a height of 0.5 meters. The kinetic energy, right? 1/2 times the mass times how fast it's moving, and it says that it's moving 0.3 meters per second up there at the top. So when you start figuring out the energy, if I take 0.5 times 10 times 0.5, we find out that it has 2.5 joules of gravitational potential energy at position B. If I take 0.5 times 0.5 times 0.3 squared, it has a very, very small amount of kinetic energy. Where did all that energy come from? It came from the spring. So 0.5 times 0.3 squared, that means that I have 0.04, oops, I said 0.04 and then I didn't write that. So 0.045 K equals all this energy over here on the right. So I can go through and solve for the spring constant. And I get that the spring constant must have been 56.055555, so I'm going to round it to 2 decimals. And the units for spring constant are newtons per meter. So the spring constant was 56.06 newtons per meter. Let's look at situation B. So for situation B, it says that there's friction, right? And so we want to figure out how much further does the spring need to be compressed if at situation B, it's still moving at the same speed, still at the same height, but some of the energy was lost to friction, and it says that 1 joule of energy was lost to friction. So we've got, and notice here that our spring isn't in our system. Well, we're going to have to put the spring in the system if we're going to solve for the 1/2 kx squared. So instead of doing work by the spring, we're going to go back to our 1/2 kx squared. Right, the negative work done by friction was 1 joule. The kinetic energy, well, before up here, right, it was moving at 0.3 meters per second, and it was a mass of 0.5, and we figured out that it had 0.0225. We found that over here, right? That it had 0.0225 joules of kinetic energy, and at that height it was 2.5 joules of gravitational. So we really don't need to calculate that out again. We can just continue to use those numbers. So our kinetic energy was 0.0225. Our gravitational energy was the 2.5. And so our object is going to end with that same amount of energy of 2.5225 joules of energy total, but it lost that 1 joule to work. And again, the K we're keeping from what we had in the previous problem, and we're looking for that x squared. So doing the math, right, if I move that 1 over, my 2.5225 ends up being 3.5225. I'm going to divide by half and divide by 56.06, and that gets me 0.12567. Well, that's what x squared equals, and remember we want x, so I need to take the square root of that number, and that gets me 0.35, and it's how much it was compressed, and the standard units there is meters, so it needs to be, the spring needs to be displaced 0.35 meters now, where previously it was only displaced 0.3 meters. So it had to be displaced a little bit further because we lost this 1 joule of energy because of friction. That's it. Hopefully these 3 problems filled in any gaps that you still had from the other examples.